Okay, hi everyone. I'm Benjamin. If you don't know me, Morteza's friend, and I appreciate Morteza's invitation. For me, I'm a guest lecturer this session. I really appreciate. Thank you very much, Morteza, because this subject is very exciting to me, and I really enjoyed talking about it. I hope you also enjoyed learning about it. I think it's so exciting that you want to come and dance when you see how interesting it is. Okay, so let's go over this. So camera model. In this session, we are seeing various aspects of camera models. And this is fundamentals of the computer vision. So you should know about this when you want to learn about computer vision, machine vision. Machine vision and computer vision are interchangeably used for the same field of science. Okay. So first off, let's talk about pinhole camera and perspective projection. By the way, feel free to interrupt me and ask whenever you have questions. So a pinhole camera models camera as a point in the 3D space. So what do we have? Whenever we have a camera, whether it's just for taking picture or recording video, right? Because video, you can see video as a stack of frames, images, right? So we have 2D image as shown here, and we have 3D objects, right? And the 3D objects are projected on the 2D image. And so we have a points in 3D space, and we'll have corresponding points or pixels in the 2D image, right? Okay. In other words, we have some lens of camera is considered as a 3D point. Locate the lens of camera lens, or it's also called optical center. That is also a 3D point in the 3D. So we have 3D objects. We have the camera, which is in the 3D space. So the object has 3D coordinates. The camera itself has 3D coordinate, and the image that the camera generates is 2D, okay? We usually, in computer vision, we consider camera to be one point, okay? Although it's not one point, it's big, but if you consider it as one point, then it is called pinhole camera, okay? Because it's like a pinhole. And as you see, camera flips the image exactly as it is done in our eyes. So when we see something in our back of our eyes, it's flipped, okay? So the whole world is flipped in our eyes. And this is exactly what is done in a camera, and it is flipped twice. Why? Once in this way and once in this way. So once left to right, it's like mirror. When you look at yourself in the mirror, it's flipped right to left, okay? And once top to down. So it's exactly flipped in this way too. So twice. And also the distance between the lens, camera lens, which we consider as one point, that's why we call it pinhole camera. The distance of the lens to the image, we call it focal length, denoted by F, okay? So when you tune your how much you want to zoom, you're changing this focal length, okay? And so you're moving like that, you are moving the image to the image back and forth, something like that. So there is a problem here, and that's the flipping. Let's simplify the model. How? The model that we saw, it flips the object twice, right? Flips the object. Not to have flips, we can modify the model to this, to have this figure. So what is it? Let's move the 2D image from behind the lens to in front of the lens, so that it will be between the lens and the 3D object. Okay. It's kind of similar to what is happening, but in this way, we will eliminate flipping. So consider this triangle, assume it is in 3D. Okay, so this is in 3D. This is the camera lens, and let it be at origin for now. Okay, origin in 3D space. Okay, so we have X, Y, Z representing the 3D space, right? And we have the object, 3D object. Let it be the frame or the image or some negative, whatever you call it. And then this will be a smaller version of this will be projected on the image. And how do I obtain this projected image on the frame? By just drawing lines from different points of the 3D object toward the lens. Then wherever they interact, they cut the plane, the image plane. That's the point that they are going to be projected to. So this, I'm moving from this point toward the lens. I cut the plane here. Also from here toward the lens, I cut the plane here. I can do it for this point too. I will cut it here. So this will make my image. Now, so usually when in 3D space, we have X, Y, Z, but in 2D, they denote it by Y, U, and V. Usually, but sometimes I've seen people who represent X, Y, Z of 3D by capital X, Y, Z, and a U, V in the image by small X and Y. Note that there is no Z in the frame, right? It's 2D. So, but usually we denote it by U and V. And why do I draw it in this way? Because assume this is an image. We usually consider this point, top corner point, as origin, the image. And this is U, this is V. Okay, in this way. So top corner is 0, 0. And here it will be the largest U and the largest V in bottom right. Okay. So I think I talked about this image enough. Now consider the same figure that I showed you in a smaller version above. Okay, I'm gonna use Thales's theorem, also called intercept theorem. In geometry in high school or middle school, we learned that. Do you remember? Thales's. So we have here we have Y. For example, consider this point that I just made it bold. This point. Do you agree that this is the Y of this point in the 3D space? Because the origin is here in the 3D. Origin is at the lens, okay? So this is Y, and this is V. So corresponding point is here. Also, the origin of the U and V is here. Assume it is the somewhere in the image. And then this is V. This is V. So this is the V corresponding to Y. V is in the image, Y is in the 3D. Now also I have focal length, which is the distance of the points on the distance of the image frame to the lens, right? This is F, the focal length. We also have Z. What is Z? This is exactly, consider this point. This is Z, right? We have its Y, we also have its Z. Now, Thales's theorem. Let's consider this. V, which I talked about right now, V over Y equals F, which is here, over Z. This is Thales's theorem for this triangle. This is a triangle. This is Y, this is V, this is F, this is z, right? Okay. Similarly, we can write it for u over x equals f over z. Similarly. Now rearrange the terms. So u will be f times x over z. V will be f times y over z. Okay. These are called perspective projection of 3D object by the camera onto the image plane. It's obvious, right? It's exactly we calculated. Okay. In these equations, x, y, z, and u and v are all in millimeters, right? Because especially in physics, whenever you say something equals something, their dimensionalities should match. If you have time at the left-hand side, the right-hand side should be time. If it is time squared, it should be time squared. If it is time over meter, it will be time over meter. That's why here I didn't change the dimension, so the dimensionalities should match. Therefore, we know that x, y, z are in millimeters in 3D, right? Therefore, u and v must be in millimeters. In millimeters. So what do I mean by u and v in millimeters? It means that in the image, when I point at a pixel, what is the distance of this point from the top top left corner in terms of u and v, in terms of millimeter. However, I want in the image plane, I want it to be in terms of pixels, rather than in millimeters. Therefore, I will divide this side by s. And what is s? S is the millimeter size of every pixel. So every pixel has some distance from its neighbor pixel, right? And that distance can be represented as in terms of millimeters. And s is that number. So in this way, I'm changing the dimensionality, so that what? U and V will be in terms of pixels, but X, Y, and Z will be in terms of millimeters. Okay. So that's obvious, I think. And by the way, S depends on the resolution of the image, right? The bigger the S, the lower resolution you have. Okay. We assume that the origin of the image is the top left corner of the image, right? I told you. Now we can translate the origin of image to be in the middle of the image. Okay. So I want the middle of the image to be the origin for my image. Let the coordinate of the middle of the image be OU and OV. Okay. When I have this, it means transpose, because I usually consider columns to vectors to be column vectors. That's why I put transpose, because it will be like this: OU and OV. Okay. So assume this is the. So what do I mean by this? It means that here, this distance is OU in terms of pixels. This is OV. OU pixels here we have, and OV pixels we have here. Okay. Therefore, in order to have this translation, I can add OU and OV in the right-hand side of what I had. Okay. And OU and OV are in terms of pixels. Why? Because we talked about it. By division by S, this became in terms of pixel. This also became in terms of pixels. Okay. So we have OU, we have OV, we have F over S, and we will see what these are. Okay. So we found these, right? We found this so far. We can restate these equations. How? Let's see. Divide the sides by Z. And what is Z? X, Y, Z is the 3D coordinate of the 3D objects, right? Okay. So by Z, then this Z goes away in the denominator. Here I don't have it anymore, and I will have times Z for OU. Okay. Similarly for this Z goes away, and I have Z here and also here. Right? Okay. Now let's consider these z's to be lambda, where we have replaced the scale z with an arbitrary lambda as a scalar. We will see why we are doing this. You'll see it's used a lot in this lecture. We'll see that. Okay. This is intuitively why are we doing that? Well, assume you have 2 points, x1 and x2. There are several ways to write an equation of the line passing through x1 and x2. One way is this, exactly this, that I have written here. x1 plus lambda x2 minus x1. What is x2 minus x1? It's a vector going from x1 to x2. This is x2 minus x1. Okay? And when I starting from x1 with this vector, now sweep lambda. Lambda can be positive, can be negative. If it's positive, it will go toward this. If it's negative, it goes toward this. So it's a line passing through it. And why am I doing that? Because I have some optical ray from the 3D object toward the image and also toward the lens. I want to find this line. By changing lambda, I will reconstruct this optical ray. Okay, that's the intuition behind that. Okay, so now we have these two equations. We can write it as a system of linear equations. We do that a lot in camera models. We write them as a system of linear equations. Okay, so I have lambda here, lambda u, equation 7, consider equation 7. Lambda u equals, what is that? Let's multiply. So it will be f over s plus x. So f over s times x plus 0 times y plus ou times z. Also 0 times x plus f over s y plus ov times z. And this is exactly what we have here. So this first row is for lambda u, and the second row is for lambda v. Exactly equations 7 and 8. I stated them as a system of linear equations. Okay. So in camera model for computer vision, we usually add a fake dimensionality. This is also a technique used a lot in camera models, and we'll see that. We add a fake dimensionality to be able to go back and forth between scaling and not scaling by a scale lambda. Okay, and I show you how we go back and forth. We see that a lot in this lecture. So the coordinate system with the fake dimensionality is called homogeneous coordinate system. Without the fake dimensionality, let's call it Cartesian coordinate system. So Cartesian coordinate system, homogeneous coordinate system. And homogeneous coordinate system is denoted by a tilde on top of the vector notation. So consider this. UV, these are in terms of pixels, right? I can write it as a vector U. Note that this is bold. Okay, and these two are scalars. So this is a vector. When I denote it by bold, I mean vector. And that's so a vector of U and V. Then I have a tilde. I add a fake dimensionality 1. Also, consider the 3D object. X, Y, Z. I can denote it as a vector X, bold X sign. Then with tilde, I add a fake dimensionality. So here we have Cartesian coordinate system. Here, these are homogeneous coordinate system. Okay. Okay, I think so far clear. When we have lambda u tilde, we can simply extract the unscaled u again by dividing all elements except the additional fake dimension by the fake dimension. So I want to go back and forth between Cartesian coordinate system and homogeneous coordinate system. Okay, so I have u tilde. I want to go toward to obtain u. What do? So this is u tilde, right? And I have some lambda here, which is a scale, lambda u tilde. So the terms will be lambda u, you can multiply this scalar by the elements of the vector. So lambda u, lambda v, and lambda. Okay, then what happens? I want to find the Cartesian coordinate system, so I ignore the fake additional fake dimensionality, which is the last one. However, I divide all of the elements by the last element, by the fake element. So I have lambda u over the fake element, which is lambda. I have lambda v over divided by the fake dimensionality lambda. Then these lambdas cancel each other. I will obtain u with uv, which is the vector u, right? The vector u. This is Cartesian. This was homogeneous. Homogeneous. Yeah. As you see, we can go back and forth, right? So whenever I have u and v, I can write it as lambda u v1. Whenever I have lambda u v1, I can obtain uv, obviously, right? So it's, although it seems simple, or kind of ridiculous, but it has its uses. We'll see. Okay. So the perspective projection, which was equation 9, I think I have repeated equation 9 here. This was perspective projection. Do you remember? We called it. So we had lambda times u and v, and we had this. Let's go back and for you to recall what I am talking about. This was exactly the system of linear equations that we talked about, okay? So I'm just repeating it here. Can be stated in homogeneous coordinates. So this is Cartesian. Let's make it homogeneous. So I'm adding the fake dimensionality 1 here, okay? Then it means that this is, the left-hand side is 3 by 1. Therefore, the result of the right-hand side should be 3 by 1 too. So this is 2 by 1. 2, let me think, 2 by 1. Yes. So this times the whole thing, and then this times the whole thing. So 2 by 1. But I need to have 3 by 1. Therefore, I add this row, and I have the fake dimensionality here too. So this becomes u tilde, this becomes x tilde, right? And as you see, everything matches. Everything matches because these zeros, it means that I ignore this. I don't care about that. So I'm adding this column too, right? Because this is fake dimensionality. And yeah, and why do I put 1 here? Why do I put 1 here? Because I want to have lambda equals z. Okay, this is what I want. So I want lambda to be equal to z. Therefore, I put 1 here. As if you put 1 here, let's simplify that. Exactly, I have simplified it here. So I will have f over s times x plus ou times z, right? Just multiply this matrix by this vector. We will have, for the second row, we'll have f over s times y plus ov times z. And for the third row, we'll have z. Here, in the left-hand side, we have lambda u, lambda v, and lambda, right? So this lambda equals z. And also, lambda u equals f over s x plus ou z. And lambda v equals f over s y plus ov z. Do you agree with equation 14? That's exactly equation 13, obtained by equation 13. Okay, now, so usually in camera model, we know lambda. Why? Because we want to go back and forth between Cartesian coordinate system and homogeneous coordinate system. So we usually know lambda, and usually, not all. Lambda is z. Okay, and what is z? It's a depth in the 3D coordinates. In the here, what we have, the 3D objects. Okay, now okay, so let's take a look at that. I'm dividing this by lambda. So this lambda goes away. This will have lambda in the denominators. Okay, now let's see. So I'm repeating it here, this term here. Why did I write it Oh, okay. Now I'm replacing lambda with z because of this, because lambda equals z. So I'm replacing lambda in the denominator by z also here. These two z's cancel each other. I'll have OU here, and I will have f over s times x over z. So far clear? Now let's talk about v. Here I have it. I divide the sides by lambda. I will have these two lambdas in the denominator, and the lambda here goes away, which was multiplied by v, goes away. And then I replace lambda by z in the denominators because of this. So I will end up with this. Okay. And what are these? These two. Try to memorize them because I want to go back. These are exactly equations 5 and 6 again. Where we started. Okay. These are equations 5 and 6. And now I think it's justified for you why I wanted lambda to be equal to z. But I wanted to obtain equations 5 and 6 again. Okay. So pay attention that lambda equals z here. Okay. Now rotation and translation of camera. Okay. So far we assumed that the camera is at the origin of the 3D space and it's not rotated. So it's neither rotated nor translated. Now let's talk about it. If the camera lens or optical center, different names for the same thing, is not exactly on the origin of the 3D space and its axis is not aligned with the axis of 3D space, it means that it's either rotated and or translated, we need to correct its position by rotation and translation. That is by an affine transformation. Okay. You usually will see later that what is affine transformation, but we usually, whenever we have a combination of rotation and translation, we call it affine transformation. Okay. So here I have x, y, z, but I multiply it by a rotation matrix. This is rotation matrix, and small r's stand for its elements, R11 to R33. Why is it 3 by 3? Because this is 3D space. Okay. And x, y, z. And this is the translation vector, tx, ty, tz. Translation in the x direction, in the z, in the y direction, and the z direction. Okay. So I can write this rotation matrix by capital R and this translation vector by bold T. Okay. So R and T are the rotation matrix and the translation vector respectively. Okay. The above equation can be stated as this. By the way, after this rotation and translation, I have this x prime, y prime, z prime. Okay. So the above equation can be restated as this. As what? So this is exactly what we have in the left-hand side. This is the, now I can bring this translation vector inside the matrix. How? So this is the rotation matrix that I had. I add a new column for the translation vector, and I add a fake dimensionality 1 for the XYZ. Okay. Then you can see it's exactly equivalent to equation 15. If you multiply the matrices and the vectors in equations 15 and 16, you will see they are the same. Okay. So I have the matrix R. I put translation vector as a column vector next to it. I also have this. Okay. And now you see why homogeneous coordinate system is useful, because of these things. We added effect dimensionality and it was useful for us for having R and T next to each other. Okay. This also can be stated in homogeneous coordinates. How? I can, although this vector is homogeneous coordinate system, I can make this matrix also homogeneous. And this vector left-hand side also homogeneous. So this was already homogeneous. I'm not doing anything to it. But I want this left-hand side to be homogeneous too. So I add effect dimensionality 1 at the end, x prime, y prime, z prime, 1. Okay. And then I add these zeros and 1 here. Why do I put zeros and 1 here? Because 1 should be equal to 1. The 1 in the left-hand side should be equal to 1 in the right-hand side. Okay. So as you see, I put transpose 0 vector here in the bottom, also a scalar 1 here. So far clear? Okay. So equation 17, we have it. Now, we'll get back to equation 17. But let's talk about the rotation. So in 3D, we can have various types of rotations. We can have different types, okay? Every rotation can be decomposed into 3 possible rotations. We have 3 possible pure rotations, okay? Either it's around x-axis, or y-axis, or z-axis. If you might have a combination of them. So might have rotation around x-axis and then z-axis. So if you see it has become like this. So around x-axis, z-axis, total it has become like this, right? But you can decompose it into 2 rotations. Or we have 3 pure rotations around x-axis, y-axis, z-axis. Why 3? Because it's 3D. So Rx, Ry, or Rz, and you can memorize it in 2D. This is the rotation matrix: cosine minus sine, sine cosine, and theta is the angle for the rotation. And when it is in 3D, but it is pure, this becomes like this. This becomes 1, and these are zeros. Or for around y, we have these as constants, and then cosine minus sine again, sine cosine here. For Rz, these are constants, and we have these again here. Okay. And as you see, whenever it's, for example, around x, the x-axis is constant. Whenever it's around y, the y-axis is constant, okay, because it shouldn't rotate for y itself. Around z, the z-axis is constant, and the rest is the same as rotation in 2D. Why? Why it's the same as rotation in 2D? Because when you're rotating around one of the axes, for the other 2 axes, it becomes 2D. Okay. These 3 rotations are named pitch, yaw, and roll. This is very important for cameras, especially in robotics. If you go to a robotic company, you hear these words a lot: pitch, yaw, and roll. So pitch, like what? So assume, consider I want to rotate my head. If I put my nose up and down like this is pitch. Okay, my head. So pitch. Now yaw. Nose moves from side to side. So this is yaw. So this was pitch, this was yaw. And roll, ears up and down like this. As you see, 3. So pitch, yaw, roll. And this is also used a lot in moving objects, such as airplanes. In aerodynamics, they have these concepts too. So pitch axis, roll axis, y-axis. Consider a plane. The plane can rotate in this way, which is pitch. Can rotate in this way, which is yaw. Can rotate in this way, which is bad for the plane. It shouldn't do that much unless it is for a jet. Then it will be roll axis, right? In control theory, if you go and see, for example, for simple airplanes for moving people back and forth, they control it in a way that they have less amount of roll. But if it is for military, then they loosen it so it can roll a lot. Okay. Then perspective. Okay, so equation 13. Let's go back to equation 13. What was equation 13? Let's take a look at that. Equation 13. Do you remember this? So lambda u v1 equals f of this equals this. Okay. This equation 21. So lambda u v1, we have this, and we have it. I think I'm repeating that. Can be stated for a rotated and translated. Oh, the difference of this equation 21 and equation 13 is what? I have replaced x, y, z, and 1 by x prime, y prime, z prime, and 1. Why? Because now I assume that the camera might not be at the origin. Okay. So now, what do we have? What did we find for x prime, y prime, z prime in equation 17, I guess? Yes, it was this. Right? So we have some rotation and possible translation. And this is now x, y, z one. Right? And we had these two as here. So far clear? I think equation 22 is clear. Now we can simplify equation 22 to become 23. How? How? I get rid of this row because it's useless for me. Now it's useless. Okay. Why? Because 1 here, this is 0, 0, 0, this is 0, 0, 1, and this is 1. I can get rid of the whole row. The whole, give me a second. These 3. I can get rid of these 2, sorry. I apologize. These 2. Multiplication of this column with this row is useless. I can get rid of that. Note that this is 3 by 4. This is 4 by 4. This is 4 by 1. So the whole thing becomes 3 by 1. This is also 3 by 1, which makes sense. But if I get rid of this column and this row, this becomes 3 by 3. This becomes 3 by 4. This becomes 4 by 1. Still, it is 3 by 3. 3 by 1, which is correct. But I have gotten rid of some extra row and column. Okay. So I simplified equation 22 to 23 by dropping this column and this row. Now, I have repeated what we found here. Let's interpret it. Interesting. Very interesting. What do we have in the left-hand side? UV1, which is pixels in the image. What do we have in the very right-hand side? X, Y, Z1. By the way, these are in homogeneous coordinate system, these two. X, Y, Z, and 1. What is that? The 3D object. So it's kind of showing how the 3D object maps to the 2D image using these two matrices. And let's talk about these matrices. What are they doing? Okay, so by this, what are we doing? The third term is a matrix of camera model, which brings the 3D coordinate of the camera lens to the, let me think. Yes, this, I'm talking about this. It brings, this is the rotation and translation matrix, which brings the 3D coordinate of the point to the 3D coordinate of the camera lens. Okay, so it considered that we might have some translation and rotation of the camera. This matrix does that. Okay, compensates that for us. Okay, so if my camera is at the origin without any rotation, I don't need this matrix anymore. But if it is, then I should compensate that. After this compensation, it seems that when you do that, it's like that you have put the camera at the origin without any rotation. Okay. Now, using this, you bring that unrotated, untranslated 3D coordinate to the 2D image using this. That is why this matrix will see that. It's called intrinsic characteristics because it brings the unrotated, untranslated 3D coordinate to 2D image. This is exactly the intrinsic characteristics of the camera. This is extrinsic characteristics, the rotations and translations, because it's not inside the camera. You have moved the camera in the 3D space, okay? So very interesting. You have two mappings in 2 steps, 1 and 2. The first step brings the camera in the origin without any rotation. The second step, which is this, brings the 3D coordinate to the image. Interesting. Okay, the parameters f over s, u, ou, and ov are intrinsic parameters, and we can name it as intrinsic characteristics matrix, K, denoted by K. Also, the other one is extrinsic parameters, which has rotation and translation, okay? And as you see, these intrinsic parameters has only f over s, ou, and ov. The other ones are zeros and ones. So these only three things are the intrinsic parameters, and the rotations, we have 9 of them, and tx, ty, tz, 3 of them. These are extrinsic parameters. Okay, so far clear. Now, combination of these two, multiplication of these two matrices is called mapping matrix, denoted by M. So this is K, and this is the rotation matrix, and this is T. Right? Okay. Now the mapping matrix, what does it do? Maps the 3D coordinate of a point in the 3D space in terms of millimeters to the 2D coordinate of a point in the 2D image in terms of pixels. Do you remember? We compensated by division by S here in the intrinsic parameters. We changed the millimeters to pixels in the image. We already did that. So we have 3D millimeters to 2D pixels. Okay. So now let's talk about camera calibration. So you have some camera, so you buy some camera for your company, but you place it somewhere. For example, you are doing some operation by your company. So it's a brand new camera. You place it somewhere, and there are objects in the scene, right? You need to know both intrinsic and extrinsic parameters of this camera in order to know how to work with it. Yeah, for now, you can see the whole mapping matrix all together. But later, we'll see that how to find intrinsic and extrinsic parameters separately. But let's first consider all of them together. So we'll have, so this is 3 by 3. This is 3 by 4. So the whole thing is 3 by 4. Mapping matrix is 3 by 4, right? M, Ij stands for the ijth element of matrix M. Okay. Now let's find, by camera calibration, we mean that let's find these parameters, M's. Okay, let's find that. So if you place this mapping matrix in what we had, we'll have equation 27. If you put in equation 23, so we have lambda uv1, this mapping matrix, and xy z1. Okay. Now consider this technique is used a lot in camera calibration. Consider a pair of actual point x1, z, y1, z1. Why do I have transpose? Because I consider vectors as column vectors. And corresponding image points, u1, v1, right? What do I mean by pair? For some points, I can myself know that this is a point. I also have my camera. It gives me some frame. I know this pixel. I can see where it is. So in the image, I know where it is. I know it's u and v. I also in the 3D, I can measure. I can consider some origin in the 3D space. I can also consider calculate x, y, z. So I know x, y, z in the 3D space. I also know u and v for that point, corresponding point in the image. So I can have some pairs. Although it's hard maybe to do it for a lot of points, but at least for a few points you can do that. Okay. Putting the pair in the above equations, what does it do? So let's simplify equation 27. Lambda u1 for u1, we are considering for u1 v1. Lambda u1 will have these times this, right? Lambda v1 will have this second row times the column. Lambda equals this, the third row times the whole column. As you see here, lambda equals this. Okay, so using this now we can go back to Cartesian coordinates. How? So we have this, I have repeated them. Do you agree that here, rather than lambda, I can put this? Rather than lambda also, I can put it here. So I have two equations. How many parameters do I want to find? 3 by 4 equals 12 parameters in the mapping matrix, right? In the mapping matrix. These were what we wanted to find. 3 by 4. 12 parameters we have. Each pair that we just discussed gives us two equations, right? We have 12 unknowns. Each pair gives us two equations. So hence we need 6 pairs of actual points and corresponding image points. Each pair gives us 2 equations. We need 12 equations for 12 unknowns. Therefore, we need 6 pairs. Okay. So when you want to do camera calibration, you only need to consider 6 pairs. 6 points in the 3D and the corresponding pixels in the image. Okay, interesting. So you don't need to do it for a lot of points. Only 6 is enough. Interesting. Okay, for calibrating a camera. Okay, now equation 28, which we found here, let's rearrange it. So bring one side to the other one. We'll have these can be rearranged as this. Okay, by these equations, we can write all equations of the 6 pairs in a linear system of equations. So these are our unknowns, and this is the matrix of the coefficients, right? So A will be 12 by 12. The odd and even rows of matrix A are these. So these are the odd ones, these are the even ones. I goes from 1 to 6. This is the index of the pair. Okay, 1 to 6. Index of the pairs. And as you see, I'm rewriting this in this way. So here, X, I, Y, I, Z, I, it means that the X, Y, Z of the ith pair. UI, VI means the U and V of the ith pair. Okay. So here I have M11, X1. So M11 is the first element, X1. M12, Y1. M12, Y1. M13, Z1. M13, Z1. I don't, in this equation, I don't have any M2 something. So these are zeros for them. Also have minus M1, M31, X1. Sorry, minus M3, minus X1, U1, M31. M31 is here. So I have minus X1, U1 as the coefficient. I have minus Y1, U1 for M32. M32 is this. I have minus UI, YI, UI, etc. You can do this for the second rows too. So even ones too. Okay, because we have two equations, right? That's why I have made it odd and even. In simple words, you don't need to make it complicated for yourself. You for every point, for every pair, you have these two equations. Do it for 6 pairs. You will have a bunch of equations. Then you write it as a system of linear equations where the unknowns are M11 to M34. And then you solve it using any linear algebra method that you know for solving linear equations, such as Cramer's rule. Okay, there are some other methods too, such as by singular value decomposition. You can take a look at these. This is out of the scope of this course. These are in linear algebra. Okay, I think the simplest one is Cramer's rule. Okay. Finding intrinsic and extrinsic characteristics now. So far we found M1, the mapping, the parameters of the mapping matrix. Now let's find the intrinsic and extrinsic parameters separately. Okay. We have two methods. Method one. This method assumes that the mapping matrix M is already calculated. So in method one, we assume that we know the mapping matrix, but we don't know the intrinsic and extrinsic parameters separately. So this is the mapping matrix. These are intrinsic, these are extrinsic. Okay. Also, it assumes that the points we have are not noisy. Okay, we'll see why. It assumes that they are not noisy. The camera is not much noisy. We multiply the matrices in equation 26 in the mapping matrix. So if you multiply these two matrices, you will have this big matrix. Okay. And I consider this as this because these are the elements of the mapping matrix. So, for example, this means that M11 equals this. M34 equals this. Okay. Now we define, this is our definition, Q, let this M11, M12, and M13 transpose, so a column vector, be Q1. This, its column vector, be Q2. This as a column vector, be Q3. Okay? And these are known. Q1, Q2, and Q3 are known because we assume that the mapping variables are known. Okay? As these points are assumed not to be noisy, the rows of the rotation matrix are orthonormal. This is one of the properties of rotation matrix. Okay, one of the properties of the rotation matrix, which was in 2D, it was cosine minus sine, sine, cosine, is this. The rows of the rotation matrix are orthonormal. And its columns also. By the way, I assume they are not noisy. If they are noisy, then the rotation matrix is not orthonormal. Okay. So then, meaning that the vectors, these vectors, what are these vectors? These are exactly the rows of the rotation matrix, right? But in column, as column vectors, right? R1, R2, R3, the three rows of the rotation matrix. These are orthogonal, so they are perpendicular to each other, and each have unit lengths. Okay. So now I'm going to use these, you will see. So second L2 norm of R3 is 1 because it's unit length. So this is by definition of L2 norm. Therefore, I can square the sides. I will have this. Equation 32, I will use that. Okay. Also, R1 is perpendicular to R3. So R1 transpose R3 should be 0. Okay. Therefore, summation of R1J and R3J, J goes from 1 to 3 is 0. I'm going to use equation 33 too. Okay. So what did we have? We had this. You remember? We had this in 2 slides ago. Okay. And we also defined these Q vectors. Okay. Now, using some inner products and these ways, and the property of that we found that they are orthogonal, some of them are orthogonal, we can separate some of the variables to find them. We can, how should I say it in English? We can bring it to the side, some of them, and the other one to the other sides, and you will see. Okay, for example, Q1 transpose Q3. Q1 transpose Q3. Let's see what happens. What is Q1? This is Q1. This is Q3. What do I mean by Q1 transpose Q3? Multiply their elements one by one. So it means that this times this R31, this times this, and this times this. This is exactly what the summation that I wrote. These are what I had in the first row, and these are what I had in the third row. Okay. Now, interestingly, all of these terms goes away. R1J and R3J, they are orthogonal. In the previous slide we just showed. So those go away. Only I have this. Okay. I can bring OU out of the summation because it doesn't depend on J. And then summation of R3 J squared. This is exactly a squared L2 norm of R3J. And that's 1. Therefore, I will have only OU. Okay. Now, OU therefore equals Q1 transpose Q3. OU exactly is one of the intrinsic parameters. We just found it. Now let's see how similarly we are going to do it for OV. So we have Q2 transpose Q3. What is Q2? It's here, right? This is the second row. So Q2 transpose Q3, I do it the same. So these two, their inner product goes away. And I will have this OV bring it out of summation. You will have OV only because L2 norm of R3 is 1. Then OV is Q2 transpose Q3. Okay, interesting. Now Q1 transpose Q1. Let's try that. So the elements will be multiplied by themselves. So I will have the elements squared. Okay. Then I use the binomial theorem. So A plus B squared is A squared plus B squared plus 2AB. So this is squared plus this is squared plus 2, the first and the second one. Okay. Interestingly, this goes away 0 because they're orthogonal. So I'll have only these. Then again, this summation can be broken to 2 summations because of this. And then for the first summation, this is a constant, comes out. And this will be the L2 norm of R1, which is 1. So I will have F over S squared. Well, similarly, I will have OU squared because L2 norm of R3 is also 1. Then, as you see, where did we start? Q1 transpose Q1 equals this. Rearrange that. F over S becomes square root of Q1 transpose Q1 minus OU squared. Interestingly, we already found OU. Let's put it here. Okay. So what happened? What is this? F over S, one of the intrinsic parameters. So we had 3 intrinsic parameters, OU, OV, and F over S. We found all of them in this slide. Assuming that we know the mapping matrix. Okay. Now let's talk about extrinsic characteristics, right? What is it? TZ we know is equal to M3, 4. Correct. And now what do we have? M1, 4. This M1, 4 equals this, right? Rearrange that. It will be TX equals S over F M1, 4 minus TZ OU. Okay. Now, what do we have? We already found F over S. So S over F is its reciprocal. I put it in the denominator. I'll also have this. M14 and M34 are known. OU, we found it in the previous slide. So we calculated what? T of Tx. What is Tx? One of the extrinsic parameters, right? For translation. Likewise, I do it for M24 equals this. What is M24? M24 is here. Rearrange it. We already have found it. Put it here in the denominator. We know M24, we know M34. OV, we found it in the previous slide. So TY is also obtained. Okay. TZ also was obtained here. So TX, TY, TZ, all of them for translation were found in this slide. Okay. Now, let's find intrinsic and extrinsic characteristics method 2. Okay, so we talked about method 1. This method first considers some valid random value. So this is iterative. It doesn't assume that we know the mapping matrix anymore. Okay, it doesn't assume. Well, how does it do that? It assumes something for the intrinsic parameters, finds the extrinsic parameters, goes back and finds the intrinsic parameters, then goes back and finds the intrinsic. So it alternates between finding intrinsic and extrinsic parameters. It's called, in optimization, it's called alternative optimization.
I have a question.
Yeah.
So for the mapping, are they even given, or do you find them using camera calibration?
You can find them using camera calibration. Why? Because mapping is not just only intrinsic. For intrinsic, maybe they can be given by the factory, but extrinsic, it depends on where you put your camera.
So is this where?
Yes, exactly. Yes, exactly. The checkerboard that they use for the camera calibration, this exactly is for finding those 6 points. Because the finding corners, why do they do that, by the way? Why do they use checkerboard?
So it has equal, it has known sizes and known distances.
I agree, but assume I don't want to use ruler and these things. It's hard for me. I can, because when I put it in the 3D object, I know where it is. For X, Y, Z, it's not hard to find. But whenever I move my camera, I will have different images. Okay, it's hard for me to manually find where those points are in the frame. So the issue is finding them in the frame. In the 3D object, it's fixed. Okay, they use some corner detection algorithms, such as, I think, Hoff transform and these things. There are some Hoff corner detection and some algorithms. It's very easy to find corners on the checkerboard. That's the reason they use checkerboard, because they don't want to manually find the corresponding pixels. Okay, the corresponding UVs. That's the reason. Okay, now we were talking about method 2. So what were we saying? It updates the intrinsic and extrinsic parameters iteratively using alternative optimization. Consider a pair of actual point x1, y1, z1, and image point u1, v1 in terms of pixels, right? So we have this by equation 23. Okay. Now, for this iteration of alternative optimization, I assume I know k, right? For this iteration. So left multiply k inverse to get rid of this k. I will have k inverse. I denote this, define this k inverse u1 v1 by u1 prime v1 prime. K inverse u1 v1 1 is u1 prime v1 prime 1. Okay, therefore I replace this by this. Okay, and the right hand side I have it without the pain in the neck k, because I multiplied k inverse. So let's simplify this into 2 equations. This is exactly because we know that lambda 1 equals what? Equals R31 x1 plus R32 y1 plus R33 z1 plus tz. And if I put it, and also I have lambda 1 u1 prime equals this times this, and I replace lambda 1, which I found. I rearrange the terms, I will have this. I'll do the same for the v prime too. So I'll have 2 equations, right? Do you agree? I use the same thing that I did before. So I have 2 equations. I'm repeating them here. Every pair provides 2 equations, as we saw. Okay. There are 12 unknown extrinsic characteristics. So we need 6 pairs again here. Okay. And then we do the same like what we had the discussion before. And we will have a system of linear equations for 6 pairs. Then we can use such as some linear algebra methods, such as Cramer's rule, to find what are the unknowns here. All of these are unknowns, the extrinsic parameters. R11, 2 up to R33, also Tx, Ty, Tz. So R1, R1 to R3, R1, 3, TX, R2, 1 until T1, TY, R3, 1, R3, 2, R3, 3, and TZ, all of them. So we found this in this iteration. After calculating the extrinsic parameters, it's time to fine-tune the intrinsic parameters. Okay, consider a pair of actual point again and a corresponding point pixel. So I will have this. Now I want to find this matrix. I found this from the previous iteration. Okay, so I can define the whole thing, this multiplication, as x1 prime, y1 prime, z1 prime, because this is 3 by 4, this is 4 by 1, so the whole thing is 3 by 1. Okay, so I end up with this. Again, we can write a system of equations. As you see, we have a lot of system of equations in camera model. So lambda times 1 equals z prime. Lambda is found. Then we also know lambda u1 equals z prime equals this. And by the way, lambda, we all know that it's z1 prime. Therefore, I can replace lambda with z1 prime. So I rearrange the term, it gives me this. Likewise, I have lambda v1 equals this times this. So it gives me this. And I can replace lambda with what I found here, z1 prime. I rearrange this, it gives me this. Okay, again, two equations. So we found these, I'm repeating them. Therefore, for every pair of actual point and corresponding image point or image pixel, we have two equations. The unknown extrinsic parameters are what? F over S, OU and OV. The rest of the terms in the intrinsic matrix are 0 and 1, constants. So only three unknowns we have: F over S, OU, and OV. So we have these unknowns. Therefore, how many pairs do we need? How many pairs do we need? I think we need only two pairs. Two pairs are enough because every pair gives us two equations, and we have three unknowns. Okay. And you might be wondering, okay, there's one thing. A can be 4 by 3, can be 3 by 3. When A in this system of linear equations is 4 by 3 and we have three unknowns, this is an overdetermined system of linear equations. There are some theories for it in linear algebra. You might find when you have less amount of equations than the unknowns, you cannot solve it. When they are equal, you can solve it. When there are more, you might find a contradiction. Okay. If you can either consider 2 points and one of the equations of 1 point, or you separate these 4 by 3 matrix to two 3 by 3s where they have shared rows, some shared rows. So for example, consider equation 1, 2, and 3. Then also one time consider equation 2, 3, and 4. You solve two systems of linear equations, you average their solutions. So this is also used a lot in camera models. When you have more number of equations, feel free to use all of them. At the end, you take average of the solutions. It's also good. Why? Because it makes you robust to noise of camera. Okay. So you solve it using any method such as Cramer's rule. I think it's a good time to have a break, if you agree. And we come back at 8:25. At 8:24. It's 8:09, so 8:24. I think it's 15 minutes. Okay, thank you. Thank you. Thanks. Okay, everyone. So just before we continue, the corner detection that I mentioned, I said half transform was something else in computer vision. Harris corner detection. So we have some algorithms for edge detection such as Previt, Solo, and canny edge detection. These are famous ones. For corner detection, I think the most famous one is Harris corner detection. And as you see, they use checkerboards to find the corners of the where is my mouse cursor? Okay, to find the corners of the checkerboard, and in this way they easily find the corresponding UVs in the frames. Because as I said, XYZ is easy to find because it's always fixed in the 3D coordinate system. We know where we have put it, but in the frame, depending on where we put the camera, it changes, and we don't want to do it manually, so you use Harris corner detection, for example. Okay, let's continue. So depth inference from images. What do we mean? So using several images, probably with different perspectives, viewpoints, and even with different cameras. It's interesting. Using several images with different angles, and even maybe with different cameras. It can be one camera moved to that side, or with different cameras, that's fine, from the same scene, but it should be facing to some same scene. We can infer the 3D coordinates of the scene. What do we mean? So we have a bunch of 2D images. Let's find the depth from these 2D images. That's interesting. So we have 2D images which don't have any depth, but when we have several of them, we can infer the depth. We have it biologically in our bodies. How? We have two eyes. We have two lenses. If you cover one of your eyes, you will not find out the depth. You can try it at home. Put one of your hands on one of your eyes, cover it completely. Then ask a friend to bring pen back and forth, and you try to grab it. Initially, sometimes by chance you might get it, but after a while, you will not understand the depth. You will lose depth. I have tried it myself. I thought, no, with my one eye, I can't find out depth. No, you can't. By two eyes, you can find depth. Okay, so that's one thing. Assume, oh, by the way, for example, your eyes are not correct, so they are facing outwards, okay? Then only in the middle range, they are overlapping. So one eye is looking at this side, one eye is looking at this side. In the middle, they have overlap. Only in this middle, that person can find out depth. Interesting. Okay, in these areas, they can't. That's one thing. Okay, so we need several images. Assume we have K images taken by either one camera or K different cameras with mapping matrices M1 to MK. If they are with the same camera, M1 to MK, they are equal, okay? So assume we have pairs of actual points, X, Y, Z, and corresponding image points, U1, V1, U2, V2, until UK, VK transpose. Why do I have only one actual point? I'm facing the same thing. So this is one object in several images. So I have U1, V1, U2, V2, until UV, UK, VK. Okay, in the K images. According to equation 23 that we had, you remember the mapping thing. So we have XYZ, one, we have only one XYZ. So in all of them, we have one XYZ. With different mappings, M1, M2, until MK, I have these ones. Lambda 1, U1, V1, 1, lambda 2, U2, V2, 1, until lambda K, UK, VK, 1. Okay, the unknown variables are X, Y, Z, while UI, VI, and MIs are known. So we know M's, we know U1, V1s. The unknown variables are X, Y, and Z, where Z is the depth, okay? In addition to depth, we can find out X and Y in the 3D object. As seen in the above equations, the system of linear equations for each image provides two equations. Why? Exactly, we already talked about it several times. This is two, although it might seem three equations, but you have lambda 1 is cancelled out. So you have lambda 1 u1, lambda 1 here equals the last row of m1. Then you will have lambda 1 u1, the first row m1 times xyz1. Then you will replace lambda 1 with with the last row of m1. So you will have only two equations for u1 and v1. Okay, you will have, we talked about it several times in this lecture. So as you see, each of them is given two pairs, two equations. So okay, each pair is given two equations. How many unknowns do we have? Okay, let's first talk about it. I think I already have mentioned it here. But for example, lambda I, consider the ith camera or the ith image, okay? Then lambda I equals the last row of that M. Let MSTI denote the stth element of MI. What is MI? The mapping matrix for the ith camera or ith image, okay? Then lambda I will be this. Simply, I'm writing this matrix format as the equations. And then I have lambda I ui, this, the first row times x, y, z, 1. And then I will replace lambda I with what I found here. So this is one equation. I do the same for lambda I vy. This will be the second equation. So every pair is giving me two equations, okay? Therefore, every image provides every image. By every image, I have one pair in the pixel and one XYZ in the 3D object. So every image provides two equations. There are three unknown variables, X, Y, and Z, right? Okay, hence two different images are sufficient for inferring depth. Why? As I said, we have three variables. Each image gives me two equations. So 2 times 2, 4. At least I need two images. This explains why with one eye we can't infer depth. Because one eye gives you two equations, right? Two eyes give you 4 equations. You have 3 unknowns. Okay, so you need at least two different images, right? Two different are sufficient for inferring depth and 3D coordinate of the scene. The system of linear equations is this, right? It's four equations, but as I said again, it's overdetermined. You can either take 3 of them, or you can sample several linears of systems of linear equations, then take the average of solution as the final solution. This is good because it will make you robust to noise of cameras, right? Okay. Then equation 49 can be solved using any method such as Cramer's rule. You see, ideas are being repeated, but different for different applications. They are not for the same thing. One of them was for camera calibration. One of them was for depth inference. Okay. Depth inference from images. As we saw, we should do this for all pixels of images. What we just talked about, that was for one image, one point in the 3D object and corresponding pixels in the images. But that's one point. What if I want to do it for the whole scene? Then I will need to do it for all of the points and all of the pixels. It's time consuming. Can we improve it? Can we improve its time complexity? Yes. Rather than two images. Oh, by the way, an interesting point is this before I tell you the technique for improving the time complexity. So I said we have two images, right? We have, for example, two images from the same scene to infer the depth and 3D coordinates. Okay, but rather than two images mean two cameras, right? Rather than two cameras or two images, I can have a projector and a camera, right? Projector is the reverse of camera. It emits light. It doesn't get light. But I still have some pixels in the projector, right? So I can have projector, and I also find the corresponding pixel in the camera. So projector emits some light to the scene. The camera gets that light from the scene and records that, okay? So rather than two cameras, I can have a projector and a camera. That's one thing. And there is a technique for improving the time complexity that I told you. And that's called using a structured light, which improves the time complexity. It was proposed in 2003, it was groundbreaking, yes. It was groundbreaking in computer vision, and it was proposed in 2003 by Schwarzschild and Sueski. This is what this reference to is one of the most important papers in computer vision in camera models. Okay, this method uses a structured light images which are similar to Haar wavelets. What are Haar wavelets? You know wavelets? They are like this, like similar to sine and cosine and these things. Take a look at that. Haar wavelets are like this, rectangular. Okay, so with different frequencies. These are Haar wavelets. Haar wavelets are used widely in computer vision. Why? Because it's hard to have smooth things in computer vision. You wanna have rectangular regions in the image, okay? And then you can have filters of rectangular things. For example, such as this. You will have in this part, you have 0, in this part, you have 1. So you have something like this. This is, you can see that Haar wavelets, and Haar wavelets have been used for face detection. It's called Viola-Jones face detector. Take a look at reference 4 and you will see more about it. Okay, Haar wavelets have been used for face. So it has been used a lot in computer vision. Also here, similar to that. It is, and these structured light images, which are similar to Haar wavelets, they are iterative method. What do they do in each iteration? The projector emits two opposite rectangular light structures, such as this. So once it divides the image into two parts, one part 1, one part 0, one part black, one part bright. The image 2 is opposite. Okay, the camera takes 2 images. Then the camera takes the 2 images. So once projector does that, camera records it. Then projector does the opposite. The camera also records that. So we have 2 images. We subtract the 2 images as image 1 minus image 2. Okay. Then in the subtracted image, whenever we have positive pixel, that means that it's in image 1. If we have a negative pixel value, it means that it is in image 2. Okay. Then in the different iterations, they fine-tune the structure. So initially it is like this, then they increase the frequency. So they do it until they find the depth, they calculate the depth of all pixels. I haven't explained the details of this method. You can take a look at the paper. I'm just introducing it to you, okay? And you will see that as it is dividing the image, the structured light structures, its time complexity is O log of P, if P is a number of pixels. But the previous method was O of P. You can see it has improved it a lot. Okay. So using this technique, you can find the depth of whole scene. Now planar scenes, camera on top of scene with known distance. What do I mean? Consider a case where the camera facing perpendicular toward the planar scene. So first off, perpendicular is important when the planar scene. So the scene is planar, doesn't have valleys and mountains. It's like plane. Why is it important? You might be thinking it's a rare case that the scene is only flat and it's planar. No, it's not. It's actually used a lot in industry, in academia, in computer vision. An example in industry which is used a lot is conveyors in factories. When we have a conveyor and some products are moving on that, the conveyor, and you have a camera on top of it. So you see, the whole computer vision in factories can be modeled as this planar scene. Another thing is that soon your camera is very far away from the scene. You are taking a picture from mountains and valleys, but they are very far away from you. That they are very far, too far that they behave like a plane. Okay, if you get close to them, it's not planar, but when you're very far away, it becomes like a plane. So these, okay, this is common case in industry, as I told you. And we can assume that the scene, okay, these assumptions I'm making, the scene is on the XY plane. I can decide where the origin is. So let the planar scene be on the XY coordinate. Therefore, Z equals 0 for the whole scene. Okay. Also, suppose the distance of the camera from the scene is D, like this. Okay. Now, according to equation 23, again, we are using equation 23 a lot, the mapping thing. So what do we have? What do we have? We have 0 here. Z is 0, as I told you. Therefore, I don't care about these things. Why do I put 0 here? When I'm planar, can I have rotation in the Z? No. Therefore, I only have rotation in the XY plane. Okay? The objects can only rotate in the XY plane. Therefore, I can simplify and get rid of, you tell me, because this is 0, as Z is 0, I can simplify this to be this. So I will get rid of this 0 row, and therefore this column goes away. So this is simplified as this. And now what have I done here? I have brought this D here. Can I do that? Mathematically, it is possible. These two are equal. You don't believe it? Multiply the matrices and you will see they are equal.
D stands for depth here.
What?
D stands for depth.
No, D is, yeah, you can see it as depth, but I think I put it as the distance of the camera, because distance of the camera and the planar scene, but as scene is planar, you can see it as depth. Okay. Assume we know the camera's intrinsic characteristics. So we'll consider both cases. In this case, assume we know the intrinsic characteristics K. We know that. Okay. We already have calibrated and we know K. So we know F over S, OU, and OV. We define the following matrix. This is K prime. Why? Because this term is D rather than 1. Okay. If it was 1, it would be K. Why? Because I want to name this K prime. Okay. Let's see. And by the way, is K prime known? Yes, it is. We know F over S. We assume that. We know OU, OV by camera calibration. Sorry about that. Sometimes this happens. So, what did we say? We know F over S. We know OU. We know OV. We know also, we know D2. We know where the camera is. So we know K prime. Okay. So I replace that with K prime. Okay. Now this is a pain in the neck. Let's get rid of that. Left multiply the size by K prime inverse. So I'll have this. It goes away here. Okay. Now, what do? I'm defining, I have this, right? I define this to be U prime V prime 1. So I can replace this with this. I will have lambda here as before, and this is the right hand side. Okay. Hence, lambda is 1. Why? Because lambda times 1 equals 0 times x plus 0 times y plus 1. So lambda is 1. Okay. And we can bring it back from homogeneous coordinates to Cartesian coordinates. I'm bringing this equation, this is in homogeneous, I'm bringing it back to Cartesian. So this becomes this. Very simple. This goes away, and also this rotation matrix becomes simplified, and I can write it in this way. What is this? Rotation in 2D plus some translation in 2D. It makes sense because it's planar. Okay, so the rotation matrix is only a rotation in the XY plane with angle theta. Therefore, I can write the rotation matrix as this: cosine minus sine, sine, cosine. Okay, so far clear? So we found this. I'm repeating it here. Okay, this is called, this transformation is called Euclidean transformation or rigid transformation. Okay. The object might be rotated and or translated on the XY plane. Okay. I think it's obvious why. For example, you have some products in the factory, they're going on the conveyor. One of them might be like this, one of them might be like this, one of them might be like this, one of them might be translated a bit here, a bit to the right, a bit to the left. So you have different transformations. There are three unknown variables. What are the theta, tx, and ty? So theta, the whole rotation matrix has one unknown, which is theta, and tx and ty. Every pair of actual points, xy, actual point in the 3D, which is planar, and the image pixel uv provides two equations, as we saw it in here in this equation. There are two equations, right? Two rows, two equations, according to the above equation. Therefore, two pairs are sufficient. Why? As I said, we have three unknowns. Every pair gives us two equations. Therefore, we need two pairs. Two pairs. What do I mean by pair? Pair of point on the 3D planar object and its corresponding pixel. Okay. Now, assume the distance is not known, because in the previous case, we assumed that the distance of the camera from the planar scene is known. But now let's assume we don't know that. Although it's knowing, it's not hard. You can meter. You can use meter to find out the distance, but doesn't matter. Now we surpass the assumption of knowing the distance of camera from the planar scene and assume that it is unknown. Okay, what do we have? According to equation 15, for the previous case, we simplified that equation of mapping and we ended up with this. Okay. And we had K, we also had D, but in the previous case, I brought D inside K and I named it K prime. But now I don't do that because I don't know D. Then this term, which is K now, not K prime, is a pain in the neck. Left multiply the size by K inverse. We'll have this. This goes away. No, sorry. This goes away here. And the K goes away. And by the way, I named this K inverse UV1 by U prime V prime 1. Okay, in this case. And then this is also the right-hand side. So I multiply all of the sides by 1 over D. So I'll have lambda over D. I'll have 1 over D here in all of the case. Okay, now if you see lambda over D times 1 equals 1. Therefore, lambda equals D. Okay, therefore, I'm bringing back again from homogeneous to Cartesian. I'll have U prime V prime, and I can write it in this way. Again, this is a rotation and translation in 2D. I can factor out 1 over D, but now this time, so this is like similar to before, but now I have 1 over D here. Okay, so I'm repeating it here. This is called similarity transformation. These are just namings in the Prince book. Okay, I will show you the references at the end. The object might be rotated and or translated on the XY plane. There are 4 unknowns now. In the previous case, we had 3 unknowns. Now, the variable D is unknown. Okay. Again, every pair gives us 2 equations. Therefore, again, in this case also, we need 2 pairs. Okay. Now I know that these 2 cases were almost similar and boring, but it's getting more complicated and more interesting. Planar scenes, projective transform, and also called homography. We will see that we're going to use them in panorama images. Okay, now assume that a camera views a planar scene, but from an arbitrary viewpoint. What do I mean? Might have some angle, right? It's not perpendicular, but have some angle. We can assume that the scene is on the XY plane, so Z equals Z is 0, right? So as I said, it's in my hand, my control, where I put the origin in the 3D space. I put it in a way that the plane, the planar scene is on the XY plane. So Z equals 0. Then Z equals 0. Again, use the mapping equation. So K, and this is rotation translation and the whole thing. But here we have 0 for Z. Therefore, because of this 0, this is simplified. So it means that this column goes away completely because of matrix multiplications. This becomes simplified. Now I define K times this matrix to be phi. And this will be a 3 by 3 matrix. So I named its elements by phi ij, phi 1, 1, phi 1, 2, phi 1, 3, etc. Okay. Therefore, I have phi here, also have xy 1. This transformation, lambda uv1 equals phi xy1, where phi is defined as in equation 57, is called projective transform or homography in computer vision. Okay. Now, again, as before, let's find its equations. Lambda equals lambda times 1 equals this row times xy1. So it becomes this. Lambda is this. Phi 31x plus phi 32y plus phi 33. Okay. Also, lambda times u becomes the first row times that. So it's this. But I can replace lambda with what I had here. Again, for v, lambda times v equals this, the second row times this, but I can replace lambda with what I found. These are the two equations. So every pair, I know this is repetitive, but it is used in different applications in computer vision. So every pair of actual points, xy, and image pixel uv provides two equations. There are 9 here, 9 unknown variables in matrix phi. These are all unknown. Phi 1, 1, 2, phi 3, 3, right? 9 unknown variables of the matrix phi. As we can find the unknown variables up to scale, this is an important thing. We can assume one of them is something and find the rest of the elements based on what we chose for that one thing. So it doesn't matter if we have a scale or not. Therefore, we can assume that its degree of freedom is 8, 9 minus 1, because it can be found up to scale, okay? You can scale the matrix phi and nothing happens, okay? Therefore, we need 4 pairs of points. 4, because every pair of points gives us 2 equations. And by pair of points, I mean pairs of actual points in the 3D planar scene and the pixel in 2D image. Okay. And again, we can use Cramer's rule or any method in linear algebra to solve that. Okay. Now, affine transformation. Affine, do you remember these? We had this, but this was rotation and this was translation in the 2D, right? Now, the rotation matrix can be any matrix without condition. If this matrix, which we consider to be rotation matrix, now it's not necessarily cosine minus sine, sine cosine. Let it be any transformation. But this is also translation vector, right? This can be any number. This is called affine transformation. So you can also see it in another way. Rather than saying it's rotation, I have said it in my machine learning course. U transpose X projects X onto the column space of U. Okay? U transpose X projects the point X onto the column space of U. And what is column space of U? It's a space spanned by the columns of matrix U, or the space whose bases are the columns of the matrix U. Okay? So this is, you can see this as projection of XY onto the column space of this matrix. But as this matrix is a square matrix, we haven't truncated some of its columns. We are projecting in the same space. Okay, in the same space. We don't go into a subspace. Okay, as we are in the same space, you can see it as a rotation. That's the reason. Usually it's called rotation. Okay. if you only consider one, rather than two columns, one column, then it will be projection onto a subspace, a one-dimensional subspace. Okay, so this is an affine transformation. This is used a lot in computer vision, this word. Panorama images. Panorama images, what are they? Have you seen them? So, you wanna have a very big image, long image of some scene, usually nature scenes. And it's hard to take one picture from this scene to capture its whole beauty. So even if you have a very wide lens, still you can't capture the whole thing. So you want to do it 360 degrees. So you can see the whole scene. Okay. So you go to a desert and you want to take picture from the whole sky. Well, wherever you go. Can you do it with one camera? No, you can't. Okay. You can take a movie or take a film, but as a picture, as a frame, can you do that? No, you can't. So you take a picture from this scene, either mountain or sky. Just imagine the beauty of nature. Take a picture, then shift the view. Take another picture, shift the view. Take another picture, shift the view. You can shift also in this way. Different rotations. Pitch, row, yaw. This. But these images should have overlap. Okay. So this, you don't do this and this. No, you do this a bit, but these two images have overlap. They have overlap. You have a bunch of images which have overlap. Now I want to stitch them to each other. When you stitch them to each other, then wherever you go, you can see. Okay. Similar, I think, to Google Map also, I think, uses that too. You can go and see the streets with different views. Okay, so panorama images are made of multiple images which have overlap, and we put them together so they can reconstruct a wide range of scene all together. So far, we were taking pairs of actual point and corresponding image pixel UV, right? So far, we were doing that. For panorama images, we take pairs of image pixel in one image and corresponding image pixel in another image. Do you see the difference? So far, what did we do? We usually used pairs of points in actual 3D space and its pixel in the frame. Now in panorama, I say I have two images from the same scene. They have overlap. Also, some parts are not in the overlap. In the parts where they have overlap, some pixel of this image correspond to some pixel in the other image. These two corresponding pixels is a pair. It's a pair. Rather than a pair of pixel and actual 3D points, now I use a pair of pixel and pixel. One pixel in one image and one pixel in another image in the overlap range. Okay, in the overlap. So in panorama images, we assume that the scene is planar. Why do we this also? This is one assumption made in panorama, and this is valid. You know what? Which is justified because either the scene is actually planar, or the scene is very far away from the camera, so that it becomes like a plane. It behaves like a plane. Now you see why many of the panorama images are from the nature. Because nature is very far away. Mountains, when you take picture, mountains very kilometers away, right? They behave like a plane. Now that is why most panorama images are from nature scenes, which are very far away from the camera. Don't you want to dance because of exciting? So therefore, we can use a projective transform or homography, which we described for panorama images. And as you really remember, in projective transform or homography, the camera doesn't need to be orthogonal to the scene. Therefore, I can have an arbitrary viewpoint. Okay. According to equation 56, we found for homography. Consider these two. I'm repeating equation 56 for the two images that they have overlap, right? Image 1 and image 2, lambda 1, u1, v1, lambda 2, u2, v2, but we have one x1. What? There is one object in the shared area of the two images, one 3D object, x1. Why is it 1? Why don't have any z? Because also in homography, I assume it's planar, right? Okay, where x, y are the actual point in the planar scene, which is shared between the two images. That is, it is in the overlap of the two images. Okay, now consider one of them, one of the points, lambda 1, u1, v1, 1, phi 1, x, y 1. This is a pain in the neck. Let's get rid of that. Left multiply the size by phi 1 inverse. Okay, so this goes away. This goes away. This equals lambda 1, phi 1 inverse this. Correct? So I have this. So far clear? Now I'm taking a look at the second image. I have lambda 2, u2, v2, 1. I have put it here. Rather than xy 1, I replace it with what I found. Rather than x, so this is xy1, right? I replace xy1 by lambda 1, phi 1 inverse, u1, v1, 1. And phi 2 is from here, from here. So far clear? So again, the whole idea is that I start with one of the equations. I found xy1 from one of the equations. Then I replace xy1 in the second equation. I will get this. What is this? This is a mapping from image 1 to image 2. Mapping of u1 v1 to u2 v2, or vice versa. Now you know the corresponding pixels. By the way, for finding, so as you know the corresponding pixels between the two images, you can now stitch them. You can now stitch them. So which maps the corresponding image pixels from one image to another image. This allows us to stitch the images together from their corresponding pixels. So it's easily, we stitch these two images, then the next two images, the next two images. This reconstructs the whole viewpoint. Okay?
So
yes?
why does that position not look right?
Doesn't look right?
Like sometimes in those instances, why is that?
Because maybe the camera is noisy, or maybe the assumption of being planar is not valid for that scene.
Two pixels that appear from one image and the other image are not correct.
Yes, so as I said, there are several. So the question is why sometimes the panorama images are looking weird, are not good. So there are several reasons, I think. One of them is that we made an assumption that they are planar. Maybe that it's not planar. Maybe the camera is not far away from the scene, or actually the scene is not planar. That's one thing. Another thing is that maybe your camera is noisy. You remember? I said when you are for homography is used in panorama, right? In homography, we just solve system of linear equations. I said you will use completely determined linear system of linear equations if you are sure that your camera is not noisy. If it is, then use overdetermined linear system of linear equations and then average your results in order to be robust to the noise. So if you use homography, but your camera is noisy, then your the parameters that you find for phi 11, phi 12 to phi 33 might not be accurate. Okay, then it might result in weird panorama images, right? Yeah.
So with this panorama images, how you explain, you're using one camera, right? One camera.
You can use several cameras.
Like equal spaced or like fixed on the jig.
See, consider Give me a second to think. Give me a second to think. No, as you see, I have used phi 1 and phi 2. So if the two cameras are the same, it will be phi inverse. I'm using phi 1 and what was phi? Recall what we had in homography. Where was that? Here. Phi was multiplication of k times this rotation translation. Of course, rotation and translation of the two cameras might differ, but k also might differ. I think even if you use the same camera, still you need to use phi 1 and phi 2. Why? Because in phi, in addition to k intrinsic characteristics, you have rotation and translation, because you're rotating your camera and you're translating it. So you have to use phi 1 and phi 2, no matter whether you are using the same camera or not. But if you are using two different cameras or several different cameras for the images, then your k's also differ in the phi matrices. Okay. Any other question? No? Okay. So here, where were we? And okay, beauty of Panorama is over. Now, finding corresponding pixels in two images from the same scene. So what did we do? We did various applications with camera model, right? We did various applications. Now, one of the applications is finding corresponding pixels in two images from the same scene. Similar to what we had in Panorama, but we'll see. So consider two cameras taking two images with different angles from the same scene, okay? In the following figure, consider this figure, the left and right cameras, you can see, so assume this is like one camera facing toward this, another camera facing toward this, okay? In this section, by the way, we are gonna derive two very important and fundamental equations in computer vision. Very important, okay? We'll see that. So we have two cameras facing toward one scene. And so camera left, I call it camera left, and right camera and left camera. We denote them by CL and CR. So L here stands for left, R stands for right, okay? And I have, so they have two frames, they will produce two images. Why have I put the image between the lens and the frame? Recall slide 1. I said I don't want to have flip, right? Okay, I have the 3D object here, X, and so this X has some corresponding U, pixel U, and when I say U vector means U and V, right? Also, this the line connecting the lens to the object or object to the lens is called optical ray. This is the optical ray for left camera. Also, consider the points on this optical left. Each of them can be seen, their corresponding pixels in the right picture. So I will have U1, U2, U3 for X1, X2, X3. Okay, these are optical rays for right camera. Okay. What is optical ray? Again, the line or the ray connecting the object, 3D object, to the lens. Okay. And by the way, one of the state-of-the-art models in computer vision are called what was that? I forgot the name. Okay, sorry about my memory. Okay, if I remember, I'll tell you. So one of the state-of-the-art methods is something which I've forgot its name, and they are based on optical rays in neural networks. Okay, they are using optical rays. And by the way, let's consider a line, a hypothetical line connecting the two cameras. This line passes through the image, the left image. This will be EL, left epipole. Epipole, EL stands for left epipole. Then it also interacts or cuts the right frame. It is ER, stands for right epipole. Okay, and this line also because we have U1, U2, U3. If you put them all together, this also passes through ER. This is called, this line is called right epipolar line. Okay. The whole thing here is on a plane, and that's called epipolar plane. Okay. These are some terminologies in computer vision. Okay. Now, first, assume the cameras are normalized, so their intrinsic matrices are identity matrix. So for initially, first that we will surpass this assumption later. Assume that KL and KR are both identity matrix. What do I mean by K? It's intrinsic characteristics matrix, right? I have it for left camera and right camera. So let them be I. It means that the cameras are normalized. So L and R stand for left and right. Suppose the left camera is on the origin. I can decide the origin of 3D space. Suppose the left camera is on the origin of the 3D space without any rotation. Hence, its rotation of left is I. Means that I don't have any rotation matrix. And translation is 0 vector. Okay. Equation 23, back to what we had for mapping. It was this, right? So now we have lambda L, UL, VL1 in the left pixels in the left image. I have K, this was the mapping ML, right? Mapping, which was KL, RL, and TL. And this is XYZ1. Why don't have L for XYZ? Because it's one thing, one scene, 3D scene. Okay, then I assumed KL is I, RI is I, TI is 0, right? Then what do I have here? This is XYZ. Okay, therefore, if you see, I can, this side, I'm writing it as this. So I'm multiplying this lambda L by the terms. So lambda LUL, lambda LVL, and lambda L. And this also, this 0 goes away. 0 times 1 is 0. So you can also don't ignore it, because you want this side to be 3 by 1, because this side is 3 by 1. So I will only consider X, Y, Z. And these are identities. So they're multiplied by 1. Doesn't matter. Okay. Now I wrote it for left camera. Let me write it for the right camera. Lambda R, UR, VR1. Again, this is mapping for R, for the right camera. And XYZ is the same object, scene. Okay. KR, I assumed it is I. However, now I have R rotation and translation. I have it for the right camera, right? So far clear? I have rotation and translation for the right camera. And what are we doing here? Just let me remember. Oh, by the way, now this equation is because of equations 59 and 60. What was 59? So KR, I have replaced it with I, correct? And what was 60? I'm replacing XYZ by what I had found in equation 16. So what I found from the left camera, I'm putting it in the equation of the right camera. Okay, so I'm replacing XYZ with lambda LUL, lambda LVL, and lambda L. Okay, and this one also comes here, right? So this left-hand side, correct? I can write the whole thing here in this way. They are equal. If you don't believe me, multiply the matrices and you'll see they're the same. So we have lambda L. Lambda L comes from here. So I'm factoring out lambda L. What happened? I'm factoring out lambda L. I have RR here. These are UL, VL, and 1. Why? Because they were lambda L, UL, lambda L, VL, lambda L. I factor out lambda L, so it will be UL, VL, 1. Also have this translation vector is times 1 is translation vector, right? Okay. So This is what we found in the previous slide. I'm repeating it here. And now I can write this as UR tilde, right? This is homogeneous coordinate. I can write this as UL tilde. So, okay, I'm renaming it. Okay, now what happens? Consider this. Left multiply the sides by TR, but by outer product. Do you know outer product? We have inner product. We also have outer product. Okay. Outer product. Just if you don't know that, take a look at that. Search it on the internet. Inner product, outer product. Okay. The outer product's result is a vector. Inner product is a scalar. So TR outer product by the sides. So I'll have TR this left hand side. I have TR outer product this. TR outer product this. Okay, why am I doing that? Because I want to get rid of this pain in the neck thing. In inner product of every vector by itself is it becomes quadratic. It becomes L squared L2 norm of that vector. Okay. However, outer product of every vector by itself is 0. As I want to get rid of this TR, I multiply the sides by TR, outer product. So this goes away. It becomes 0. Okay, becomes simplified. So I'll have this, by the way, lambda R is a scalar. I can bring it out. Can go back and forth in multiplication. So I have this. Here, lambda L is also a scalar. I can bring it out. Lambda L and this. Okay. Now what do I have? Now I left multiply the sides by UR tilde, but in this time by inner product. Okay. And inner product, you can write it by transpose. Right. Yeah, cross product. Yeah. So cross product or outer product. But now I'm using inner product. UR transpose this term means that the inner product of UR and that term, right? UR, because A transpose B is the inner product of A and B. Okay. So UR transpose this, I also have UR transpose this. Why am I doing this? Because here, what is TR outer product UR tilde? Whenever you have something outer product of a vector, it's perpendicular to that vector. Okay. So TR outer product UR tilde is perpendicular to UR tilde. Therefore, its inner product by UR tilde is 0. Inner product of two perpendicular vectors is 0. Okay. I want to get rid of this pain in the neck term. Therefore, I use UR tilde transpose. So this becomes 0 and a scalar 0 because it's the result of inner products is a scalar. Here I have this. I'm repeating it. Now, do you agree that I can write it as in this way? So I bring these parentheses here. Does it matter? No. Okay. So I'll have UR tilde transpose TR outer product RR UL tilde equals 0. Let me clear here a bit so you can see this equation better because this is an important equation. Okay, equation 62. Now, according to problem 16.2 in the textbook of Prince, okay, reference 5, this TR outer product RR equals ATR RR. Here is matrix multiplication, okay, where ATR is the antisymmetric matrix of TR. Okay, you know what TR is, by the way, right? You haven't forgotten that. This is a translation vector for the right camera. Okay, so ATR is defined as this. So you will put TX, TY, and TZ of the right camera in these elements. It gives you ATR. If you multiply ATI by RR, it can be proved that it is equal to TR outer product RR. Okay. So we accept that from Prince, and then we replace what we found here by ATRRR. Equation 65 is obtained. We found this, I'm repeating it here. Now we defined essential matrix, one of the most important matrices in computer vision. Essential matrix is a 3 by 3 matrix. It is defined as TR outer product RR, or as we said, it's ATR matrix multiplication by RR. Okay? It's defined as this. It's called essential matrix. It's 3 by 3 matrix. Therefore, if I put it here, this is, then I'll have UR tilde transpose E UL tilde equals 0. And this 0 is a scalar. I think it's obvious. Why? This is, for example, U, what was U? So U tilde, UR tilde is URVR1, right? So it's a 3 by 1 vector. Therefore, this is 1 by 3. This UL also, UL tilde, is ULVL1. So it's 3 by 1. E is also 3 by 3. So the whole thing is 1 by 1. It's a scalar. This series. Okay. What is equation 67 doing? It's a map between UL tilde and UR tilde. Right? Either UL tilde to UR tilde or UR tilde to UL tilde. Doesn't matter. So it's what, and what were the UL tilde and UR tilde? UL tilde and UR tilde, you can see that UL and UR, because tilde is homogeneous, right? And what does it mean? So between UL and UR, or UL tilde and UR tilde, it means that these are the pixels in the two images. So it's a map from corresponding pixels to each other. So you map this point to another point. So you map a pixel in this image to the corresponding pixel in another image. That's very interesting. If you can find this matrix E, and if your what? Don't forget, the two cameras were normalized. We assumed that. If your two cameras are normalized, their intrinsic characteristics matrix are identity matrices. Then, if I know E, you give me one image, another image. I tell you, without blindly, I can say this pixel must be in the row 5, column 6 of the other image. That's very interesting, right? Okay. Now we surpass the assumption of normalization of cameras, because we assume that they are normal, but they might not be in real world. Let the two cameras be any general cameras. We will find another very important matrix in computer vision. Suppose the left camera is on the origin of the 3D space without any rotation, because I can decide about the 3D space, the origin of the 3D space. So again, as before, the rotation matrix of left camera is I, and its translation vector is 0. Again, equation 23, the mapping. So I write it for the left camera. So I have lambda L UL VL1 equals KL RL TL XYZ1, because XYZ is the same object for the two cameras, the same object. We don't use L for them. Like before, RL is I, TL is 0, but this time KL is not I. I have KL. It's YZ1. Okay, this KL is a pain in the neck. Let's get rid of that. Left multiply the size by KL inverse. Therefore, this goes away, and I will have KL inverse. I also multiply this lambda L by the term, by the elements. So I will have lambda L UL, lambda L VL, and lambda L, right? This 0 also is multiplied by 1. We don't care about that, because this side is 3 by 1. I want the right-hand side be 3 by 1. So I will have X, Y, Z. Okay. Now, equation. Now we write it for the right camera as before. Lambda R, the mapping thing. Lambda r is UR VR1. Then I have KR RR TR XYZ1. Again, it's the same 3D object. I don't use R subscript R for XYZ. Okay. Now, what do? I have XYZ here. Let's replace it with what I found in equation 68 from the other camera. So I will have these for these 3 XYZ. This one is also here. Okay. Let's continue. We found this. Okay. Now I can write this as UR tilde, right? Correct. And what else? I'm factoring out this lambda L. Okay. Here I have KR, RR, KL inverse. So KR, RR, KL inverse. UL tilde, which is this. ULVL1, right? Because lambda L was multiplied by 1. So I have this. I also have KR TR times 1. It's here. KR TR times 1. Right? Now, what do? This KR here, let me clean it. This KR is a pain in the neck. Okay, let's get rid of that. Left multiply sides by KR minus inverse transpose. Doesn't matter. I need inverse to get rid of that, but I also transpose that. Doesn't matter. Okay. So what happens? This goes away. Then I will have KR inverse transpose. This KR is also goes away. So far clear? Okay. Now, again, like before, I use TR outer product from the left side. So I have this, and this. Okay. Now what happens? Lambda R is a scalar, can come out, can move back and forth in multiplication. Lambda L also is a scalar, comes out. And what do we have here? TR outer product, TR is 0 as before, goes away. So I use TR outer product to get rid of the last term TR. It was a pain in the neck. Okay. Now what do we have here? What do we have? Let me remember. Okay. Left multiply all the sides by KR inverse transpose again. So I will have this. I will have this. Okay, because I have only 2 terms now. Okay. I will have these two. I'm left multiplying KR inverse transpose again. Okay. So now what do I do here? I left multiply UR tilde transpose from left. Okay, like before. So this step was additionally done. It wasn't done before, but this step and this step were done in the previous slide too. Okay, so I have UR tilde transpose, UR tilde transpose. So I'm having inner product between UR tilde and the terms. Okay, why do I do that? Because I know that this is an outer product containing UR, so it's perpendicular to UR tilde. I want to get rid of that to become 0. Therefore, I'm doing inner product of UR tilde, right? Okay, and the right hand side, I have it as before, as here. So far clear? Okay, now I can bring this parenthesis here. Does it matter? No. I bring it here. So this equation, now the equation has changed. Previously we only had this in the middle. TR, outer product RR. Now these two terms appear. KR inverse transpose and KL inverse. And now I think it makes sense to you. Because in the previous case, we assumed that KL and KR are identity matrices. If you put identity matrices in equation 770, they go away. They become multiplication by 1 is the same, by identity is the same, right? So equation, let me see, equation 62 is a special case of equation 70 when KL and KR are identity. Okay. Now so according to equation 63. So what did we say? I said according to Prince's book, TR outer product RR is equal to ATR RR. We defined ATR. It's anti-symmetric matrix of TR. Then, so I can replace this with this. Then according to equation 66, what did I say? In equation 66, that was the definition of essential matrix. What was essential matrix? This. It was ATR RR. E was ATR RR. So I'm using that here. Therefore, I'm replacing this with E. Okay. We found this. Okay. I'm repeating it here. Now I define a new matrix, fundamental matrix F. So that was essential matrix. This is fundamental matrix. This is also a 3 by 3 matrix F. This is equal to KR inverse transpose E KL inverse. Okay. As you see, F and E are related to each other. Okay. Fundamental matrix and essential matrix are related to each other. So this is one of the very important matrices in computer vision. It has even a Wikipedia. We can take a look. Okay. You can restate this as this. E equals KR transpose FKL. Why? Prove. We have this KR. This is F, right? This is a pain in the neck. Right, multiply KL. Then we'll have KF, KL, KR inverse transpose E. This is a pain in the neck. Left multiply KR transpose. Then KR transpose F, KL equals E. Exactly what we have in equation 74. Okay? So these two equations are important. They are a restation of each other. And now this was F. We defined this to be F. Therefore, this is F. Therefore, I write it as UR tilde transpose F UL transpose UL tilde equals 0. And this 0 is also a scalar because this is 1 by 3 UR tilde transpose. F is 3 by 3. UL tilde is 3 by 1. Okay. And this 0 is a scalar. As you see, equation 67 is a special case of equation 75 when the two cameras are normalized. Okay. Again, what is the importance of this equation? It maps a pixel from one image to its corresponding pixel to another image, even for any arbitrary cameras. It doesn't need to be normalized camera. Now, what if we want to find the fundamental matrix values? So how to find them? How to find F? E is a special case of F. So F is hard. When we talk about F, we can see it as talking about E2. Okay. How to find F values? We can find the parameters of the fundamental matrix using pairs again. Using pairs of corresponding pixels in the two images. It's interesting. So you have, consider these, ULI tilde and URI tilde. And what are they? In the left and right images, two corresponding pixels. And I denote them by their elements by ULI, VLI, URI, VRI. Okay. These are their homogeneous ones. So the ith pair, we have several pairs. This is the ith pair. Okay. So I put it in equation that we found for fundamental things in this equation 75. I put it in equation 75. This is fundamental matrix. All of these elements are unknown. We want to find them. Okay. There are 3 by 3 unknown parameters in the, excuse me. So these are unknown. There are 3 by 3 unknown parameters in the fundamental matrix. Hence, 9 pairs of points can be enough. Why? Every pair is giving us how many equations? Only one equation this time. Because this 0 is a scalar, right? Only one equation. So we need 9 pairs of points. Can be enough for finding the unknown variables in a system of linear equations. Note that it can be shown that the degree of freedom of the fundamental matrix is 7. See reference 5. Okay, the book. Therefore, 7 pairs are sufficient. So you can consider these are the coefficients, because these gives you some equations, right? These are the coefficients of the equations, and these are the unknowns, F11 to F33. Set it to 0. This is a system of linear equations. Use Cramer's rule or any method in linear algebra to find that. You can use 9 points too. Doesn't matter. 9 pairs too. Either 9 pairs or 7 pairs. As long as you can solve the system of linear equation, that's fine. Then you have the fundamental matrix. What is this use case? Assume you do this. So it means that what does it mean? You have 2 images. They from the same scene, maybe with different angles. You only select 9 points from this image and find their corresponding 9 points in the other image. Okay. You can either do it manually or use checkerboard and do corner detection, right? You can do that too. So either manually or using edge detection or corner detection algorithms, you find 9 corresponding points. Then this equation tells you the fundamental matrix. You find the fundamental matrix. Then using that equation, you will find all of the correspondences. After finding the fundamental matrix, you tell me where can I find this pixel in the other image? I tell you this. I can calculate it. It's here. It's very interesting, right? Acknowledgement. Some slides of this slide deck are inspired by chapters 14, 15, and 16 in the textbook of Simon Prince, Computer Vision, Models, Learning, and Inference, published in 2012. That's a very good book. That's a very good book in computer vision, especially about these camera models and these things and transformations. What?
So using this one, generate a top-down view.
Which method?
The whatever you just described, or the homography.
Okay.
When we were talking about homography, if you have, for example, a camera taking a picture of the slot of this area, can you generate a top-down view using any of these techniques, or is that impossible?
Let me think.
So the reason why I ask is because Apple has recently came up with an app called Destiny.
Yeah. So we talked. So one of the sections was the transformations, right? So
that's going to be
Yeah, the different transformations we talked about. One of them was affine, one of them was similarity one. So one of the transformations which we didn't cover was warping. Warping is using warping. You can do what Camera Scanner does. So Camera Scanner is an app in smartphones where you take some picture and it removes the angle. How? By warping. So there are several transformations, and I think that's warp. Why? Because in warping, you have two, for example, lines like this, but they should become parallel. So that's warping. In the transformation that we talked about, this doesn't happen. But there are several transformations which we didn't cover, and that one of them is warping. Yes, you can apply different transformations. Which one? Oh, these I didn't prove them. I just referenced that. There are at least I can tell you about the 8th one. Why do we need 8? Because it's up to scale. When you have 9 parameters, does it matter in equation 76 if you scale them, you multiply the size by 3 times everything becomes 0. If this is 0, 3 times this is also 0. So you don't care about the scale. So it's up to scale. Therefore, one of them you can assume one of them, and the other one will be found based on the other one. So this reduces the 9 unknowns to 8. Also, how do we go from 8 to 7? I think this is the reason. One of them here is the 1. We don't care much about it. So it's similar, it's acting similar to what we have in lambda. Lambda, because it's homogeneous, right? In homogeneous, in homogeneous systems of equations, whenever we had UV1 and lambda, it always gave us 2 equations rather than 3 equations. Because of that, I think, so one of them is because of being up to scale. The other one is because of having this 1. By the way, the question was why we have 7 degrees of freedom. And I told you the reason. What? Yes?
5.1 and 5.2 being 2 separate cameras. What would happen if there were 3 cameras?
Which slide?
It's a little bit.
Okay, I go back.
It would be 42, somewhere around.
Okay.
Yeah. So currently we have 5.1 and 5.2.
Yes.
What would happen? Because my understanding is because there's 2 cameras, right?
Yes, we have.
So you mentioned there would be still 5.1 and 5.2 if there was 1 camera.
Let me think. So here in homography, the question is why do we need 2 cameras and not 3 cameras, something like that, right?
This would have changed the equation. You mentioned that if we use 1 camera, it wouldn't change anything, right? So
yeah,
it means the same camera. This is 2 different cameras to get the images.
That doesn't matter. If we use 2 different cameras, this K changes. This rotation and translation already changes because we usually when we are talking about 2 cameras, it means that they are having different angles or something. Otherwise, they would be the same camera. So the rotation and translation change. K only changes if you change the camera too. But I still don't understand why we can have several cameras. Then we'll have several files. But something I think you didn't get it completely is that when we use that in panorama images, I'm using 5.1. What? This is a slide. Okay, 5.1 and 5.2 because I want to stitch 2 images. So if I have 3 images, then I first stitch 2 of them, then this becomes 1 image, and the other 1 image, then I have 2 images again. Nice. So I stitch them 1 by 1. Yes. Just let me finish the acknowledgement and rep because I usually go over references too. This is because, just give me a second, because I think the most important thing in the slides are the references. So acknowledgement, this is the book. The book is very important. Take a look at that. Prince is also, I think, Prince is, as far as I know, is writing a book on deep learning too, understanding deep learning, going to be published, going to be published by MIT Press. I think this is the same Prince. And by the way, we covered almost the chapters 14, 15, and 16 of this book today. Okay. Some slides of this slide deck are inspired by teachings of Professor Hoda Mohammadzade at Sharif University of Technology, Department of Electrical Engineering. Her teachings was based on Prince's book, textbook. Okay. And references, very few of them. So this is our tutorial paper on optimization, because I think once I talked about alternating optimization, we can take a look at that, our tutorial. This, what is this? High accuracy stereo depth maps using structured light by Schwarzschild and Selesky in 2003. This was one of the most important papers in computer vision. This was saying the structured light, improving the time complexity of finding depth from the images. This is a paper about Haar wavelet. You can take a look at that. A Haar wavelet transform, its status and achievements in 2003 by Stankoviev and Falkowski. This an analysis of the Viola-Jones face detection algorithms. Viola and Jones, there were two scholars proposing that algorithm. This paper discusses this algorithm. You can take a look at that. And this is the Prince's book, Computer Vision, Models, Learning, and Inference in Cambridge University Press, 2012. Okay, thank you very much. Thank you.
Sure.
Yeah.
Can you just update the slide?
Yeah. So I will give Morteza the slides, the annotated slides. Also, I will upload the video to my YouTube channel. Take a look. Just search my name, Benyamin Ghojogh, and I have two YouTube channels. One of them is about my poems. The other one is my main YouTube channel has the lectures. Okay, so you can take a look at that. I will upload that there too.
For just having some point for our present in class, I will open it with. It has just half a mark, and if you just write down anything, you get, for example, 0.25, and if you solve that, you get full half mark. So